Greetings, everyone. Time to talk about polar coordinates. One of the final things that we talk about in trigonometry, and it's a very useful system for expanding the universe of functions that we talk about. So let's start with just talking about the coordinate system in general, right? Don't forget that we graph things rectangularly by giving two coordinates like 5, -2. It means I would go 5 along one axis, 2 in another direction along another axis, and where those meet, we have a location, right? That's what a coordinate system is, a way of talking about a location somewhere on our space, right? In this case, a two-dimensional space. So the polar coordinate system is just a different way of talking about the same locations that you've been graphing for years. It's just a different way of looking at how to get to the location, right? For example, in the real world, you don't usually walk in a bunch of right angles, right? You don't go, oh, my friend's over there, go this much this way, then turn and then do this much this way. It usually doesn't work like that unless you have to go around a building or something, right? So we don't actually move in rectangular coordinates for the most part. To be honest, polar is a more natural way of doing things anyway. If you see something you like, you turn towards that object, right? Get an angle of rotation, and then you go straight towards that object. That's what polar coordinates is. Polar coordinate system is when you are given an r and a theta, right? The theta is going to be a rotation from the x-axis like we normally graph an angle, right? The standard angle system. And r is going to be a distance from the origin that you move once you are facing that direction, okay? So when I do this system, right, I rotate and then I move outward. So depending on which way I'm looking, right, it's just going to move outward from the center, okay? Now, this is a coordinate system, just like y and x, which means that my two coordinates need to be measuring quantities that are at a right angle to each other. And this is still true in polar. It may not look like it because I know the angle isn't necessarily a right angle, but you got to remember the x-axis and the y-axis are not my coordinates anymore, okay? Here's the way it works. Theta is going to rotate in some direction like this, like if it's going around a circle, right? It's going to do this. Theta is going to point in the direction that you want to turn. So theta is always kind of looking like this, right? So theta is doing this. And then what's r going to do? Once I'm rotated to that position, r is going to go outward, okay? So our coordinate system is actually always at a right angle to each other. It's just a right angle that's constantly shifting around like this in polar. So my coordinates are still perpendicular like they're supposed to be. That makes them independent. It makes it an efficient coordinate system. Okay? Now the other concern is how do I convert back and forth between the two systems? Well, we're going to use normal trigonometry, just like, in fact, it should look somewhat familiar from when you were talking about vectors. It's the same exact math. We're just applying it to locations rather than directed line segments, okay? So we still have the way of converting from rectangular into polar by solving for an r or calculating r and finding a theta, calculating a theta, and then you'd have that system. Or vice versa. If you have an r and a theta because you're in polar coordinates, then you can use r and theta to calculate y and x if you're in rectangular. And it's all based on the same trigonometry that we've been talking about all semester, right? The fact that when I get an angle out to here and I have the radius here, it forms a right triangle. I can use my reference angle, but of course the actual angle in question is the one that got us to that position, right? And then that gives us the relationships of r, theta, x, and y, okay? So an example of graphing something in polar would be if I wanted to graph 5, 200 degrees, all right? And be careful, it needs to be labeled degrees to be in degrees, right? If it just said 200, that would be 200 radians. So it's r comma theta, right? And so it's 5 is my r, 200 degrees is my theta. So I start by rotating to 200 degrees, right, into quadrant 3. And then in a straight line from the origin outward, I count 5 units, okay? Now, whenever you're graphing one of these, most of the time you'll have a different way of graphing than the x and y axis by itself. Usually they'll have polar graphing, which is a bunch of concentric circles. And those circles just represent radial distances from the center. Okay, I'll show you one in a little bit. But as you can see, this is what's actually happening. I just need to count 5 units along a straight line from the origin at that angle, right? And then I get to the location in question. And no, this point is not the same as that point. These are just 2 separate examples, okay? All right, so something to think about from polar. When you're in rectangular coordinates, something has a location and it always has a unique representation, okay? In rectangular coordinates, there's only one way to talk about a given point, okay? Polar is different. Polar is another way of looking at locations, and there's actually an infinite number of ways to talk about any location, okay? That doesn't make it more difficult. It makes it a little bit more versatile, actually. So, for example, this same point, negative 3.4 and 2, is the same point in polar coordinates 4, 5 pi over 6, right? That's 150 degrees, right? Look, there it is. There's that location, same location. But instead of going left and up, I'm rotating and then moving outward. I rotate to the 5 pi over 6 radians, and then I count out 4 distance from that center. Okay? So, mostly because of the angles, right, and because we have coterminal angles of all different shapes and sizes, that's why you can get other representations that all talk about the same point. Because remember, the trigonometry is not based on the actual angle itself. It's about where does that angle position you on the grid, right? Well, many angles can all have the same position, hence the coterminal, right? So the first one that you should see is, what if I rotate in the negative direction and get to that same line, right? 2 pi minus 5 pi over 6 is negative 7 pi over 6. These two representations are the exact same point. Okay? Here's another one right here. What if I rotate 2 pi plus the angle, right? That means go around one full circle and then still do the extra 5 pi over 6. 2 pi plus 5 pi over 6 gets me 17 pi over 6. This coordinate point in polar is exactly the same as that polar point. Okay? Now, here's the thing that we don't usually do when we're doing this kind of math, and that is letting r be negative. Since this is a coordinate system, both theta and r can have negative values because we're basically just letting the numbers be whatever is possible here. Okay? So it is actually possible to have a negative r value. And what does that mean? It means I can point at a direction with the theta, but I'm going to move away from it instead of towards it. Okay? So here's what you can really think of this as. When I'm graphing this point, I rotate first to the angle, negative pi over 6. So that puts me in quadrant 4, pointing this way. Right? But what I did was I drew not just the line into the center, I drew the line all the way through the center and to the other side. Right? Notice I just drew a straight line and it went through the center to the other side. If it had been 4, negative pi over 6, the point would be over here. But since it's negative 4, I'm moving away from the direction that theta is pointing. It's exactly anti-parallel. Notice it's in the same location because I'm using a negative r value. Okay? So by that same token, instead of doing negative pi over 6, I could rotate in a positive direction to the same line, right? See, that'd be the same negative pi over 6 angle there. But I rotated in the positive direction, 11 pi over 6. And again, I used a negative r to go in the opposite direction of the way theta is pointing, okay? So all of these are just samples of how I can have the same location even though it's a different polar representation. And it's mostly based on the fact that angles are coterminal, okay? Let's do some actual graphing and converting from polar and rectangular coordinate systems here, okay? So let's graph a point in polar coordinates here. Remember, the way we were just saying was you're supposed to rotate to where you want to face and then go straight out towards the location at the distance away. So that's what we're going to do. Now you'll notice what I've drawn is sort of like a bullseye there. And actually a lot of times when you see polar graphs, you'll even see other little lines going out at the 30 and 60 degree angles, sometimes 45 degree angles. I didn't do that because I actually have a protractor to help me here, okay? If you don't have a protractor, then you may want to try and find the paper that does actually have the other lines on it. But the circles are still important, and that's because you got to remember we're not moving left, right, up, and down necessarily along an axis that has nice numbers marked out on it. We're going to be going to some angle and moving out in an angled radial direction, right? So I need to have those circles there to show me where 1 radius, 2 radius, 3 radius distances might be. Okay, it's just the easier way to tell how far out you've gone because the circles are the same distance in all directions. Okay, so I've got this right here, and I'm going to graph this point, 3.5 comma 57 degrees. So first thing I'm going to do is I'm going to label 57 degrees, right? Okay, so I'll put my protractor centered right here, right? And we're going to find 57 degrees. Let's see, 55, 56, 57. All right. And I didn't draw a solid line. I drew a dashed one. Because I'm not interested in the line. The line is not actually what I'm graphing. Remember, I'm graphing a point. I'm just using those to mark about the angle that I should be at, right? So the angle is to here, right? This is the 57 degrees right here. And then I'm supposed to be 3.5 distance from the center. And it's positive, so I'll be going in the direction that theta has mapped out. So 3.5, 1 circle, 2 circle, 3 circles, and then, oh look, there's 4 circles, so a half would be right in between them, right here. Okay? All right. So that's the location of where this point should be. 3.5 comma 57 degrees should be about right there. Well, let's find out. Let's convert it into rectangular. That's the next thing we want to do anyway, right? We'll go ahead and convert this one as well as all of those. If I want to convert this one into rectangular, the conversions are that x is r times cosine theta, y is r times sine theta. So here we go. My x coordinate should be 3.5 times the cosine of 57 degrees. And my y should be 3.5 times the sine of 57 degrees. In this case, we'll need to punch them up in the handy-dandy time saver. Make sure I'm in degree mode this time. 3.5 cosine 57. I have 1.9. pretty close actually. And for the y value, I just hit up, change cosine to sine, and I have 2.94. I'll make this one for now. 2.94. Okay. Now the circles are up there for the polar, but they're also measuring, you know, on the axes as well. You can see, right? Right here, 1, 2, right? Something like that. You may not be able to see it right away, but if you look, this point right here is just to the left of this marker right here, which would have been the 2 marker on the axis, right? So it's just under 2 on the x-axis, and it's just under the 3 marker right here, you see? I know my point's really big. It's actually right there. It's just under the 3 marker, right? Right there. So this is the rectangular representation. 1.91, 2.94 is the point. Okay? Well, while we're on that scheme, let's go ahead and convert these other two right here, right? I want to convert negative 3.5 comma 57 degrees. Well, what's the relationship to this point from this one? It's the same angle, isn't it? But it's got a negative r. So if I rotate to this angle 57 degrees, negative r would be in this direction, right? So if I keep that same line through the center there, it should be somewhere in this neighborhood right here, right? Should be a little bit further. Should be somewhere like that. Somewhere in quadrant 3. Well, let's find out. Right here, when I convert, I'll say x is equal to negative 3.5 cosine 57 degrees. Y is equal to negative 3.5 times sine 57 degrees. Okay? And those two put together are going to give me, go ahead and, punch it up like we did before, right? If you hit all those things in there, just multiply by the negative, you're going to get negative 1.91 and negative 2.94 ish, right? Which is exactly what we're looking at right here, right? Okay, 6 comma pi. In radians, pi is what? And as far as the angles go, right? Isn't pi a semicircle right here? So I'd be going out this way, right? It'd be pointing exactly on that x-axis, and I should be going out 6 units. So we should be looking at something on the x-axis here. Let's test that out. When I convert this one, right, I should have 6 cosine of pi and 6 sine of pi for my 2 different coordinates, right? This one should be x, this one should be y. And what's cosine of pi? You're supposed to memorize that one, right? You need to know that one. Cosine of pi is negative 1. So negative 6, because it's negative 1 times 6. And then sine of pi is 0. So 0 times 6 is 0. Notice I'm getting negative 6, 0, which is the point on the x-axis over there. Okay, vice versa. Let's convert from rectangular into polar. Let's do the easy one first right here. 0, negative 2. 0, negative 2 is this point right here. And if you don't want to actually draw it every time you do these, if you want to picture it in your head, as long as you can get a good clear picture, that's fine. But you really want to be able to visualize the angle before you calculate it, because it'll help you save time. 0, negative 2 is here, and I can see that that angle is hitting the axis there, right? you're supposed to know what that angle is already. That's 270 degrees, or 3 pi over 2 radians, right? So I can already tell that it's going to be some r, comma, 3 pi over 2, right? Because that's the angle. We already can see the angle, don't need to calculate it. Well, and how far away from the center is this? It's along the axis, it's 1, 2, downward, right? So it's 2, comma, 3 pi over 2. Because it's a straight 2 distance in the direction that theta has led it to. All right. -1, negative square root of 3. Let's draw it out again. That's going to be 1 to the left and square root of 3 down. So we're looking at quadrant 3 here. All right, I'll enhance it a little bit there. So -1 and negative square root of 3 is going to be somewhere right here, right? Let me zoom in a little bit for you. So -1, negative square root of 3, which means I've got this going for me here, like that. So my theta, my angle is going to be here, and I've got my right triangle, right? The length of this right here is the negative square root of 3. The length right here is the -1. We already know how to calculate r, though, right? This right here. R squared is x squared plus y squared. So r squared is -1 squared plus negative square root of 3 squared. That's just 1 plus 3, which is 4. So r must be 2. Now, think about it. It could have been plus or minus, right? We don't want to do the negative r unless I'm going in the opposite direction. Okay? So my r is 2. And then let's calculate the theta. And once we finish converting all these, we'll come back and do the rest of this problem here. Okay, so I've calculated my r. How do I get the theta? It says tangent of theta is y over x. Okay, we'll give myself some space here. It's saying that tangent of theta, the thing I should be looking for, is equal to y over x. That's negative square root of 3 over -1. Negative over negative is positive, right? And anything over 1 is itself. So tangent of theta is equal to square root of 3. Well, that's one of your memorized angles, isn't it? The simplest answer is that theta could be what? 60 degrees. Pi over 3 radians. Let's use radians. But that's why you draw it out either in your head or on your paper. Where's pi over 3 at? It's over here, right? This would be pi over 3 right here. That's not what we need. I need it in quadrant 3. So pi over 3 must be my reference angle. It's this thing right here, right? This little reference angle. I'm in the third quadrant. That means I'm going to have a semicircle plus that much more. So my actual theta, this is just my reference, right? So my actual theta is going to be pi plus that, because it's in quadrant 3. So it must be equal to 4 pi over 3. So then I'm looking at the point 2 comma 4 pi over 3. Okay? We're still in converting mode here, so let's talk about this last one. Again, we're going to calculate the r first. Go ahead and graph it out, though. 17 is going to be out here somewhere. -8 is going to be down here somewhere. So we're looking at something like that. And it's going to do this. Okay? So the angle that we're interested in is a quadrant 4 angle. Let's go ahead and do this. Right? Like this. That's going to be my theta. All right, let's calculate r first. R squared is 17 squared plus negative 8 squared. So let's see, 100, 70, 70, and 49. So 242, 89 plus 64, right? And then that's going to give me 353. Right? So R is the square root of 353. Now, of course, depending on what you're using this for, that's a completely appropriate answer to keep, or they may want you to punch it in and actually get the distance itself. So square root 353, 18.788, so about 18.8, right? Either one of those, depending on your situation. All right, now what about theta? Tangent of theta is equal to negative 8 over 17. Okay, now a tangent is equal to a negative value. Remember, that has two answers. It's either quadrant 2 or 4. And because we were smart enough to draw our point first, we know we're going to be scouting just for the quadrant 4 answer, right? If I want to do the quadrant 2 answer, that would be the other side of the line. I would have to do a negative r to make that work. Let's just go straight forward here. It's quadrant 4, so I'm going to have a quadrant 4 angle, right? And a positive r, right? Because I kept my r positive already. Okay, so my reference angle is going to be the inverse tangent of just the 8/17. Remember, we don't use negatives in arc while we're solving these. Okay, let's go ahead and do degrees this time. Inverse tangent 8 over 17. 25.2, that works. My reference angle is around 25.2 degrees. Okay, that's not my theta. I'm in quadrant 4, right? Don't forget to do quadrant 4, it's 360 minus the reference angle. So my theta is going to be 360 minus the reference angle. So theta is approximately 360 minus the 25.2. So that's 340, 335, 334.8 degrees, right? Okay, so I now have my polar coordinates there for that one. 18.8 comma 334.8 degrees. All right, so now to finish this up, I wanted to keep on the roll. You know, we were on a converting roll there. It asked for other representations of the same point in polar here. Okay, fine. That's not too hard. One of them has to use a negative r. One of them has to use a negative theta. Okay, so to do a negative r and still land on this location means that I have to get theta pointing in this other direction. I have to let theta point this way so that my r will go opposite, fight against him. So if my theta is going to point this way, then I need a line somewhere out here, like this, and I'm going to need my theta to rotate all the way around to this line here. Okay? But the symmetry of this thing shows me that this 57-degree angle is here, and it's also down here in quadrant 3, kind of like a reference angle, almost exactly like a reference angle. Okay? So this is 180 degrees right on the axis. So this line right here would be 180 degrees plus 57 degrees more, right, by the symmetry argument there. So I've got 237 degrees for that line. Okay, if I rotate to 237 degrees, he's pointing this way. I would have to go opposite in order to get to the same location. So that requires a negative r. So my first new representation is going to be negative 3.5 comma 237 degrees. And don't forget, you can check yourself on this. Put in the r cosine theta and the r sine theta and see, you'll get the same location, the same coordinates. Okay, now what if we want to use a negative theta? Well, I want to get to this same line right here, right? I want to get to this line right here that we were using, but I want to do it in a negative direction. So what I'll need to do is rotate, starting going the downward direction in the quadrant 4, and I'm going to rotate around this way to hit it here, right? How much is that in the negative direction? Well, remember, a full circle would have been 360, and I almost made it. I just didn't do the 57 in the middle of the wedge there. So this angle right here is negative 360 plus 57. Because I went negative 360, but then back plus 57 back up from it, right? So that there gives us negative 303 degrees. Okay. So my other representation is 3.5 negative 303 degrees. Again, check yourself by plugging it in and seeing that you actually still get the same coordinates, the 1.91 and the 2.94. Okay. So let's look real quick at the point that we just graphed a moment ago, the 3.557 degrees. So you can see what it really looks like on the grid here. GeoGebra can draw it way better than I can. What I have built here is something that will rotate the angle, and then I can also draw the radial length outward. Okay, so here's what I'm going to do. I'm going to let it play so that I can first do my angle, so I can get to 57 degrees. Whoops, too far. Right, already went too far. Let's say 57. Right, okay. So it's at 57 degrees now, as you can see, and it's supposed to be a radial length of 3.5. So that means I'm going to let my r travel to, whoops, 3.5. Okay? Notice the coordinates of the point A right here. Right? That's exactly what we computed, the 1.91 and 2.94. Right? It's traveling along this line, which is the 57 degree angle representation, and then you can actually see the segment there. So if I just get rid of the line for a second, you can see. And then of course, if I get rid of the segment, this is actually what you should be seeing when you graph a polar point, just the point. Of course, these other representations help us, find these points like this. Next, remember we found another representation of this one with a negative r, and that representation was letting the angle rotate all the way around to this other side here, right? Okay. So if I do that, I would have to let the angle rotate to here. Now what you're going to notice is if I let the angle rotate here, this dark line that I have drawn right here is actually going to be right back where it is now. But what I need to have is theta pointing in this direction. Then what I'm going to have to do is rotate this thing to 180 plus the 57, right? Which is the 237 right there. Okay, so notice the 237, right? But then r would have to be negative. Negative 3.5. Again, look at the location of A. Look at the coordinates of A. It's
left exactly the same point, but I've represented it differently, right? I've rotated it to here and made r negative.
Polar coordinate system is not just useful for points by themselves. You have to remember that all of the graphs that we make are collections of points. So if I can convert a single point into a polar representation, I can actually convert an entire graph the same way, with the same trigonometry, the same conversion equations. I would just have to convert the equations that I'm using to graph the shapes in rectangular into equations that are represented with the polar r and theta variables instead. And I can actually get the same shapes. Now, of course, some shapes are going to work better in polar and some of them are going to work better in rectangular. That's the reason why both systems are still around today. We use both systems for different situations. I want to show you two graphs here that you've seen in rectangular probably quite a bit, and show you how some of them are good in polar and some of them are good in rectangular, depending on what kind of shape we're talking about here. Okay, so 2x minus 5y equals 10. I want to convert this equation into its polar representation. Okay, now the points use the direct conversion. The equations are going to be using kind of like a reverse, because I'm not converting numbers here. I need to convert the variables themselves with what they're equal to. So it's going to be the opposite conversions from what we were just doing. Instead of converting with the r squared equals x squared plus y squared to go into polar, here I have an x and a y variable, and I know what those are equal to. X is equal to r cosine theta, y is equal to r sine theta. So I'm going to convert it that way. Okay, so look right here. I have 2r cosine theta minus 5r sine theta is equal to 10. Okay, so I'm technically in polar form now. I have converted x and y information into r and theta information. But just like our functions in rectangular, we like to have one variable isolated and then all of the gobbledygook on the other side as the function calculation. So to do that here, I'm going to start by factoring out an r that they have in common. And I get 2 cosine theta minus 5 sine theta, like so. And then I want r by itself. That's typically what we do in polar. We get the r variable isolated because the theta controls the direction. Remember, you always graph that first. Which way am I pointing? And then I go outward. So theta typically is the independent variable and r is the dependent. Okay, typically. Right here, all I got to do is divide this big value to the other side. So I have r is equal to 10 divided by 2 cosine theta minus 5 sine theta. Okay? So this is the equation in polar form. If someone were to ask you to convert, this would be the answer. What I want to do is go through a few calculations here and show you how this truly is that same shape. Okay? So here, let me put some tools here for me to use. And actually, I want to change these numbers up a little bit to make a little bit more emphasis. Since I'm using the calculator, I can really do more than just the memorized numbers themselves. Okay, let's start with 10 degrees, then go to 30 degrees. Then, 60, and then we'll do 90, yeah. We'll jump up a little bit there, right? We'll be jumping around on these things. Okay, so I'm going to put these in the calculator. I'm picking theta numbers, and I'm just going to be plugging them in to those things using the calculator. Well, especially for the ones that are the off angles, like 10, right? Well, actually, that's the only off angle, isn't it? Okay, still. The 0 one's pretty easy though. I know that cosine of 0 is 1 and sine of 0 is 0. So what I'm getting is 10 over 2 times 1 minus 0. So that's just 10 over 2, which is 5. Okay? So what I want you to notice is that it's 0 degrees and 5 radial units, right? 0 degrees is here, and 1, 2, 3, 4, 5. Look, there it is. See, it's already on that dot right there. That's that first point. Okay? Next, I'm going to compute the next point. 10 divided by, parentheses, 2 cosine of 10 minus 5 sine of 10. And that's equal to 9.079. So like around 9.1-ish, right? Ish. We can say 9.08. Okay? So where is that at? Let's take a look at where that is. 10 degrees and a distance of 9, right? So from the center here, 10 degrees is here. 10 degrees, whoops, is right here. Okay? Now you may not be able to see it, but the ruler is how I did out all of these other things. And the ruler is actually hitting 9 right on the tip, right there. See, I'm in this direction. Right there is on the 9. Right? This is the 10-degree angle at a distance of 9, right there. Okay? Let's keep going. If I do the same thing, but I put in 30, I get negative 13. What happened? I'm getting negative number here for this answer. Right? All of a sudden it went negative. Here's what happened. My R is rotating here, right? And as it rotates, this line gets longer, right? As this rotates, it's going to be going further and further out right here. So this is at 10 degrees, it's here, right? At 20 degrees, it'll be out here. And at somewhere in there, right? Somewhere in between 10 and 30 degrees, it goes off and actually becomes undefined because it's going to go out to infinity. And then there'll be a point where it gets so high that it actually comes back around the other side of the shape here. So at 30 degrees, the theta will be at 30 degrees pointing this way, but since my R is negative, right, it's going to go in the opposite direction. So at 30 degrees, negative 13, what's happening is it's going way out here, negative 13 distance, somewhere on the line over there. Okay? As I continue to rotate higher and higher, you'll see the R will stay negative, right? So let's do 60 degrees now. Negative 3. So 60 degrees and negative 3. Let's actually map that one out because we can. Right? Let's get 60 degrees is here. And it's going to go in the negative direction. So, to go in the negative direction there, that means I'm going to put something through the center at that angle. But instead of going that way, I'm going this way. Okay, now let me line it up with the 6 here. And notice from the 6, it hits the line at 3, which is a distance of 3 right there. Right there. -3. Okay, so you can probably guess what's going to happen at the 90-degree one, right? If you plug in 90 degrees, cosine is 0, sine is 1, I get 10 over -5. At 90 degrees, I'm getting -2, which is this point right here, right? So this is what happened, right? As the thing was rotating, the point went further and further out until it actually reached infinity. That's usually not possible, right? And then it bounced back over here with the negative values and kept coming up this way. The easiest way to understand this is to think of it from what we call a projective standpoint. From a projective standpoint, imagine you're looking at like the surface of the earth, right? And you're watching an airplane go around. What's going to happen? The airplane's going to go around the back of the earth at some point. And then what? It's going to come back around this other side. That's exactly what happened here. As this thing rotates and goes further out, it goes around the other projective side of the map. It comes back up on this side and then finishes drawing the rest of it with negative radii, right? So that's why it's important to have the ability to do those negative r's. Theta was pointing this way, right? But the actual line should have been down here, and it actually accommodates that. As you may have been able to tell, this isn't exactly the best in polar form, right? It's actually a rather complicated function in polar form, right? It's a straight graph. It's a line, right? Polar's more curvy, more circular. So, of course, lines are going to be not jiving well with polar coordinates. Let's switch over here. Look, in rectangular coordinates, x minus 2 squared plus y squared equals 4 is a circle. The center has been shifted 2 to the right, not shifted in the y at all, with a radius of 2. So shift the center 2 to the right, and the radius is 2. And I get a circle, right? Things that are circular like that probably work really well with polar. Let's see. X minus 2 squared plus y squared. So what I'm actually going to do here is I'm going to FOIL this out. X squared minus 4x plus 4 plus y squared equals 4. All I did was x minus 2, and multiply it out, right? I get this. Notice I can subtract 4 from both sides. And I'm going to rewrite it like this. Okay, almost ready. I'm going to add the 4x over like this. X squared plus y squared is one of your equations, one of your conversions, right? X squared plus y squared is r squared. And then x is r cosine theta. To finish out solving for r, what I'm going to do is divide both sides by r. Technically, you shouldn't do that because you might divide by 0. Technically, what we should do is move this back over, factor the r out, solve each separate equation. But you get r equals 0 as one of your solutions, which is not possible. R equals 0 is just the center dot on the origin. It means r is 0 all the time. You never leave the origin. It makes no sense. So what I typically do just as a shortcut, and it's sloppy, mathematically you're not supposed to just divide by a variable because you could divide by 0. But we're excluding that. We're saying the r is not going to have that result, right? What you'll notice is that I get r is equal to 4 cosine theta, okay? Whether you factor and solve it out, or if you divide and go sloppy, you know. This is the polar form. Notice it's quite simple, right? R is just equal to a cosine function, right? And you'll notice the number in front is the distance here, right? Double check me here, yeah. Yeah, so look, when theta is 0, cosine of 0 is 1, right? So you'll notice on the axis it goes out 4, right? And then as I rotate, it shrinks. And then at 90 degrees, cosine of 90 is 0. So at 90, it hits this. And then cosine becomes negative in quadrant 2, right? So as soon as cosine starts going in this direction, as soon as theta starts going in the second quadrant, the r starts going negative. So then even though theta is pointing this way, the graph starts mapping out this side because it does negative r values. And then it finishes out by the time theta is at pi. Okay? So that is the polar form of this circle.
Here's a much better view than what I could draw on a board. GeoGebra has a way of being able to have things in polar form. As you can see, the polar grid looking like the bullseye we had on the board there. And what I've got set up here is a couple of different things. I've got the blue dashed line set up to be the direction that the R is going to draw a point in. I've got the red theta dot line right here that's going to show up. That's going to show the current direction of theta at all times. And then I've got the green points here that are going to draw out the shape. I'll give you a quick sample just so that you can see what I mean. Right? The point right here is the starting point. It's going to stay there unless I move this slider. So we actually don't even really need that one for now. Okay, so as you can see, what's going to happen is the blue dashed line is showing where R currently is for this particular theta. The thing that you might see at some points now is theta will point in one direction and R will point in the other. That's going to happen when R is negative. So let's start over. Notice the equation over here, 10 over 2 cosine x minus 5 sine x, is the line that we were just graphing a moment ago in polar form as we calculated it. So what I have here is for you to see the order in which this line is drawn in polar form. And it has everything to do with the way that we define our angles to start from this axis and rotate in a counterclockwise direction. So keep your eyes on the theta and r as the line's being drawn. Right there. It went off the scale, off to infinity. And look, theta is still pointing this way, right here. Theta is still in the first quadrant, but it hit that point where r is negative, so it's got this huge distance of r coming on this negative side, which is completely opposite, anti-parallel of theta. Let's continue drawing. See, as theta rotates, r is still negative, and look right there. Right, this is one of the points we calculated, right? It has theta is 90 degrees, or pi over 2, and then the r is negative 2. It's pointing the other way from it. And as theta continues to rotate, you'll see it wants to eventually meet up with the other side. And right there. Notice theta is at pi. It's done a semicircle, and throughout that whole entire period it had the r values to draw the entire line of 2x minus 5y equals 10. Okay? The other graph that we were looking at, I'm going to do here. Again, notice the polar grid, right? We have the concentric circles here. And it's the equation of 2 cosine x. Remember, we just calculated that. Should be a circle on the centered around the x-axis where the center is at 2. Right? Oh no, that's right. We did 4. That's right. That's right. We did 4. That's better. Okay. So let's see here. Let's go ahead and let it draw. Notice r is shrinking as theta increases. And then it finally goes through the center, and then look, right there. Right after it passed the center point, you see theta is still in quadrant 2, but r started being calculated as a negative number, right? So it's r is pointing in the other direction of the theta. And then it meets back up with our other end there, right as, whoops, went too far. We can do this. See 3.14, right? And then it's the complete circle there.
So let's go in the other direction now. Let's take something that's in polar form equation and convert it into a rectangular equation, right? So sometimes this helps us understand what a polar equation is trying to do. Other times it's just we need to convert it back because rectangular works better. It just depends. Okay, so r equals 3. Very straightforward polar equation. Just r equals 3, right? Think about what that means for a second, though. It means that no matter what theta is, r is 3. So at every angle theta, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3. What shape does that make, right? Think. 3 in every direction. It's a circle centered at the origin. Let's calculate it. Watch. If I square both sides, r squared equals 9. But remember, r squared is x squared plus y squared. And that's the rectangular equation for a circle of radius 3 centered at the origin. Right? Okay. Theta, no r. Theta equals 3 pi over 4. Right? What does that mean? It means theta is always this angle. But r can be anything it wants, right? So it ends up being a line. You pick a certain angle, and then you let r be whatever it wants. But theta never changes. For this one, do a tangent of both sides. Right? Now, of course, tangent 3 pi over 4, you're supposed to know that. That's tangent of 135 degrees, right? That's in second quadrant, so -1, right? Okay. But then tangent theta had an equation for it. It was y over x, right? Tangent theta is equal to y over x. Multiply both sides by x, and y equals -x. Notice that's the line that goes through the origin with a slope of -1, like this, right? So theta is 3 pi over 4, always. And then r can be whatever it wants. Little less obvious. R equals 5 cosecant theta. Cosecant's not one of those nice ones, right? It doesn't always jive well. It's not so bad in polar. It's just one function, though, right? But it's hard to visualize what is this thing really doing. Okay, so for this one, write cosecant as 1 over sine, like so. Because that's what cosecant is, right? The reciprocal of sine. Multiply sine to both sides. Right? Now, r sine theta, that's just y. And now it's in rectangular form. Y equals 5 is a horizontal line, 5 up on the y-axis, right? Right? Okay. Now we saw one a little while ago that was one of the basic trig functions. We saw r equals 4 cosine theta. Remember, so the cosine theta by itself made a circle. Well, here's a sine theta almost by itself, right? It has this extra 2 added in though, right? So it doesn't exactly go as easily because it's got more than just the sine. So here's one way you can do this. What you do is you multiply r to everything. So what I have is r squared is equal to 2r plus 3r sine theta. Now 2 of those you should recognize right away. R squared is x squared plus y squared. And r sine theta is y. Right? What about the 2r though? 2 is there for sure. But what is r equal to? Well, remember, r squared is equal to x squared plus y squared. So r without the squared is still the x squared plus y squared, but I then have to take the square root of it. And that doesn't look like anything that I'll be able to solve anytime soon for x or y. It's a messy, messy thing. I'm just going to stop there and say, yeah, this shape doesn't work well for rectangular coordinates, right? Because also we didn't consider that if I do the square root on the r squared, I could get a plus or minus here, which could give us multiple answers. And in rectangular form, it wouldn't be a function. That's also something that you need to think about here. In polar form, it's 100% a function. Inputs are only used once to any given output, right? Whereas if I convert to rectangular, it doesn't count under the function hood anymore because I could get dualities. I could get multiple values for single x's and things like that. Plus, not to mention, it's a complete disaster mess of an equation, right? The shape of this guy is a limacon with an inner loop. See if I can draw this accurately enough for you here. My art skills here at work. So 2 plus 3 is 5, up here at 5, and then 2 minus 3 is -1. So right here at 1. I know I said -1. Just watch. The shape that you're going to get is going to go like this. And then it's going to come around and inner loop like this. Like that. Okay? So, obviously not something that we would normally put in rectangular, right? Doesn't pass that vertical line test that we're accustomed to using. In polar, it's completely a function though. 100% works as a function. To finish up, here are some curves that exist in polar coordinates that we never really draw in rectangular because they don't work well in rectangular. You already saw one. We saw a limacon that had an inner loop already, right? Here's the generic spectrum of limacons. You can have ones with an inner loop. You can have ones that are just the heart shape where it comes to a point. And you can also have the ones that are just shorter on one side than they are on the other. I know it looks kind of like a circle. My artistry skills are not the best. But here's the thing. You can tell by the numbers. When the numbers are equal, you get the heart shape with the point in the middle. When the number on the outside is bigger than the coefficient on the trig function, then you get the pieces flatter away. And then, like the one we saw before, if the coefficient on the trig function is bigger than the shifted number there, you'll get the inner loop. And the reason for this is because the number on the outside being, let's say, bigger than this right here, right? That means this 5 is always going to be bigger than what this cosine will put out. The cosine itself is trapped between -1 and 1. So this 2 cosine is never going to put out anything bigger than 2 or less than -2, right? So the 5 always wins out. So what happens is when theta is at 180 degrees, right, it goes out to the 3 there, right? Whereas if they're equal, at some point they'll cancel out to 0, hence the point at the origin there. And then when the cosine has a bigger number, it can actually overtake the 5 at some point, which makes the r's go negative. And then you get that inner loop. While theta's pointing one way, it loops inside because you get a negative r. Okay, something else? The rose curve family. Anything where you have a cosine or a sine just by itself, but there's a frequency change, the n times the theta there, okay? If you change it to say something even, then you'll get twice as many petals as you have the frequency. So 8 petals in this case, right? It goes around, and it doesn't do them in order. It doesn't do like that. It actually goes around like this. It comes through and graphs one here, and then it goes up here, and then it comes down here, and then it goes up here, and then it goes down here, like this. It keeps going in and out of theta, of r being positive and negative. So it keeps coming around and around and around and around like this until it finally meets up. Same thing with the odd ones, right? It starts over here. Well, in the origin right here, it goes up. It comes down and it grafts this one. Then it comes around like this, and then it goes up like this again. Okay? Notice if it's odd, you get the same number as that number of petals. Okay? And then lastly, lemniscate. Everyone knows that as the infinity symbol, lemniscate, right? Anytime you have the sine version, it's going to be corner to corner. And anytime you have the cosine version, it's going to be side to side on the axis. And really, what this is a subdivision of the rose curves. But the squared on the R there is making it to where half of the petals are imaginary. So we can't graph them because they're imaginary values. Think about it. Because sometimes this sign will put out a negative number. And if I were to square root to figure out what R is, to solve for R, I'd have to square root. Sometimes I may square root a negative number. It's imaginary. So there's actually, 2 more imaginary petals on each of these. They just can't be graphed because we don't have an imaginary scale there, right? It's all real numbers. So you end up with just 2 of the petals out of the normal 4 because of the 2 behind the thing. And they're always in the pattern of being, in the same angle. So you get either an angled infinity symbol or a left-right infinity symbol, or lemniscate. Okay? Well, I hope this helps you understand polar coordinates better. And I hope you enjoyed trigonometry.
So let's take another look at a couple of these curves that we have here as well. I want to talk about the limacon first here. Look, the 2 plus 3 sine x. That was one we drew in the previous section, and now we're just talking about the limacons in general. Notice that since 3 is bigger than 2, I am going to get an inner loop that will stretch a radial size of 1 away from the center, because 3 minus 2 is 1. Also, 3 plus 2 is 5, so it should peak out at 5. Here, let's take a look. Right? Now keep in mind, this whole time R is pointing in the same direction as theta, as you can see. Theta is going around. Theta is the little red dot at the unit circle mark. R is still pointing with theta. Still pointing with theta. It's going through 180 degrees. Wait, it's getting shorter, and notice right here. Boom. R is now a negative value. It's pointing in the opposite direction as theta, and that's how you actually get the inner loop here. You see? And then it's going to shrink back down, and it's going to start pointing with theta again, like so. And then it's going to meet up on the other side there after doing a full 2 pi. Right? So there's our limacon shape with the inner loop. And the inner loop is because the number by the trig function is bigger than the other number, right? Now what would happen if I were to change that other number like 2 to something bigger than 3? I bet you're wondering. I'll do that real quick. Notice if I do that, I get a limacon still. 4 is bigger than 3 now, so I don't get the inner loop. It never actually goes negative when it's drawing it. Okay? Notice as it's going around, right? As this thing is going around, R never actually goes negative to point in the other direction from the theta. So in this particular case, R stays with theta as far as the direction, the sign goes, S-I-G-N sign, right? And that's also a limacon. Okay, so now let's take a look at the lemniscate, the infinity symbol here. And since you notice I did a cosine one, and you see the square root. Basically what I had to do here was solve for R. Technically the lemniscate should be R squared is equal to. I had to actually solve for it. It has 9, so it should have a radius of 3 at the maximum points, and then the 2 is what gives it the leafy pattern there. All right, so here we go. Now watch this. R is gone. Look at theta rotating. Theta's rotating, and then boom, R just all of a sudden pops out again. Do you see that? Now watch this. It's going to happen again. Boom. Theta's rotating, rotating. Still no R. Now there's R. Did you see what happened there? In the spots in between the petals, right about, in this region right here, you see where theta is rotating, there's no R. It's not that R is 0. This is one of the two regions where R is just imaginary. So for this graph, it's not really defined. So theta is just rotating, and you're not getting anything that you can graph for R. Hence why we only get the two leaves, which then look like a lemniscate. All right, let's take a quick look at a rose curve too. I've got 3 cosine 5x. Since 5 is odd, you can expect 5 petals. If it had been even, we would have double, right? Watch the pattern that it grows out. It doesn't just do one petal after the other in the order of theta rotation. What happens is, since the frequency is increased so much, the cosine goes in and out of being positive and negative a lot more often as it goes around. So watch R switch signs, SIGN signs, as this thing rotates a lot. And R is now negative. And now R is back positive again. Negative. See, it keeps switching. That frequency of 5 is going to make R keep switching back and forth way more often than it ever normally would have. And boom. For this particular one, it finished in pi, right? It actually got the whole shape done, and it met back up with this other piece when theta was equal to pi. Okay, so let's do one more thing here. Let's change it to 3 cosine of 4x. So since 4 is even number, remember we can expect double, so 8 petals. And the reason you're going to get the 8 petals, by the way, is because it doesn't meet back up with itself as quickly as the odd ones do. See, you can tell it kind of starts off the same way. And it's going around the petals between being negative and positive R. But you see, it's not meeting up with that other endpoint, even though theta just passed up 180 degrees. It just passed up pi. So in this case, it's just not able to meet up with that other end until it goes around the whole thing. In which case, it has twice as long to graph, double the number of petals. And there it is.